This is Arun Sharma from MIDASoft. Welcome you all to this online bridge webinar presentation. And today we'll be covering the first topic of this webinar series, that is how to prepare bid winning requests for proposals. And our focus will be on post-tension box girder bridges, which are mostly design build projects. So this is what we'll be covering today. First, I'll be walking you through the usual workflow of for requests for proposals, and then what is the role of design engineers in that and how they can contribute. And then we'll be talking about how and why MIDASoft is needed. So we'll be investigating the reasons and finding out how MIDASoft can help you in preparing an efficient bid. We'll be walking you through the post-tension optimization tools, how to generate bill of material and report generations, and if you have to evaluate different construction methodologies, then how to go about it. And then we'll be summarizing what we done today and who else is using MIDASoft. So let's start with the workflow for the request for proposal. So there is an entity called owner or the client, and he puts out the project statement for preliminary design, and then a company is selected to perform this preliminary design, whom we call as client engineer. And then the client engineer prepares a design build agreement, which is phased out for requesting for proposals, and then the contractor cites these opportunities and creates a team with different components in it. So he has a team that will have a fabricator, environmental engineering firm, geotech engineering, design engineers. So he has a team with him. It's called a consortium, and from that consortium, he hands the drawing package to the design engineer, whose main job is to cross-check the data that has been given to him with the client's engineer. And then once he has cross-checked all the information, and if he is making some kind of recommendation, then he has to frequently talk back and forth with the client's engineer. Now once he has done that, then his job is to verify the criteria that are given, is to verify and optimize the post-tensioning, and if a construction methodology is suggested, then he has to verify that as well. If not, then he is supposed to propose one. Now once he has done this activity, he has to compile everything in bill of material and report, which is then used by the contractor to get the pricing, the man hours, and all the other expenditures sorted out and compiled in a presentation or a report format. Now sometimes owner wants the contractor to come up and present their request for proposal, and in that they have different proponents have to come in and give their own presentations. So request for proposal is basically a two-pole activity. One is technical, the other one is presentation. Now presentation need not always be a PowerPoint presentation. It can be a well-documented report with conveying all the details, or it can be an animation of the entire process that they've simulated. So it's all about how strong the technical checks have been made and how well it has been proposed or put forward to the owner. And this is what we'll be covering today. So let's see why MIDASoft is needed. The role of engineer that I just described can be laid down in this flowchart. So he starts by reviewing the drawing package, then he has to check the bridge type, layout, span, section which is being proposed by the client's engineer. Then he has to optimize the post-tensioning, and then he has to make recommendations, if any, and then he has to go and prepare the bill of material, report, and presentation. Now, this is the workflow of another software that will be used by the engineer to fulfill the following criteria or the following needs of his flowchart activity. So you start by creating a geometry in another product, then you apply tendons to it, then you set up construction stages. This is very important for both tension structure, and many of the products are not able to take into account the construction staging. So provided you have a tool that can handle construction stages, so you will set up the construction stage analysis. Then engineers apply the live loads and the other static loads. Then they perform the analysis, and then they perform the design. Now, if the design checks are not as per the criteria, he has to go back and redo the entire process. So while creating geometry, he has to use a different cross section this time, or if the cross section is fixed, he can alter the span lengths. If not, then he has to come and modify the tendons. And in tendons, he has to modify the cross section area, the stresses, the forces, in order to get a good and efficient design. So as you can clearly see that this process would require several iterations. This process would be time consuming if we have to perform check for multiple construction methodologies. This process would also need extra effort from the engineers to prepare bill of material and report, because that are not taken care by the current tool that we are looking at. So this is how MIDASoft kicks in. MIDASoft will provide you with tools that will walk you through the entire flowchart for your work requirement, hence making the process more efficient. So you can start by generating the model to a wizard, which will take care of your tendon layout, construction staging, and loading. All you need to do is apply the live loads and then perform the analysis and design check. While before performing the code design check, you need to first check whether I'm getting some feedback on sound. Let me quickly check that.
Great, thank you. Actually, there was some technical glitch here with the headset that I was using, so I switched to a new one or a different one, and therefore it's performing better. Alright, so continuing from where we left, so instead of going and performing the analysis and then design and then modifying your layout and tendon profile, what you can do in Midas is that you can just perform the analysis and check the tendon yielding criteria. You can see the deflections and stress values, and then modify the tendon property very easily. And then once you have got an optimal solution, you can then go ahead and perform the design checks and constructability checks to seal your iterations. So as you can see, you need not go all the way back to redo everything, but you can just take care of the entire iterations by quickly modifying the tendon property. And you can then perform the design checks and constructability checks, and then you can generate the bill of material with a high quality report. So you can see the entire work process is being supported by one tool. So having done this, let's quickly move on to a hypothetical problem that I've taken here today. So let's see how Midas will actually be doing this job for you. So this is an example of a 3-span post-tension box girder, and you can see the design build details are given as follows. So it's a straight bridge. It's the total length is 540 feet, 3-span, each span is 180 feet, the width is 33.6 feet. There are 2 lanes. Construction methodology has been proposed by the client. So let's say it's movable scaffolding system, which is the most common practice. Then you have the material properties as grade 6000 psi. Then we have the steel as A70, so low relaxation strands. And then the applied codes are as per PSC design check, as per ASH12 RFT, creep and shrinkage to be used as CEBFIP 1990. The section details are given as here. So what we'll be doing is, let me go back into the program itself and quickly start modeling. So this is the new look of Madisonville 2013 version. I'll start with a new page, and this is the Works tab, which is the backbone of this software. Many of our users that have joined in today will already be familiar with this workflow. So what I'll be doing is start with a structure wizard. That will be MSS Bridge Wizard, so movable scaffolding system. And here I'll be defining the bridge layout. So I'll start with defining the material property, and make sure the unit systems that you are working in is consistent. So I'm working in kips and inch, as you can see here. At any point of time in the modeling process, you can switch the unit system to the one that you are currently interested in. So I'll start by defining the material, click add here, and then just select concrete, standard as ASTM reinforced concrete, and the grade of concrete as C6000 psi, and then hit apply. Now I'll use the define a tendon material, ASTM standard, and then I'll use A416 270 low relaxation strands, and then hit OK. So you have the tendon property and concrete defined. Then I'll enter the span length. So it will be 3 spans at 180 feet. Now the units are inch, so I'll just multiply this value by 12 and the program will take care of it. And I have to specify where the fixed support should be. So let's say it's at the first pier. It has a fixed support. Number of segments per span being 20. Cold joint being at 0.2 of the L2, that is the second span length. And you can easily see all these variables that you have to, or the parameters that you have to enter are given, are taken from the diagram above. So I'll just enter the anchorage length S4, as you can see. Let's say it's 12 feet or 144 inches. And the diaphragm width is 144 on either side of the support. And then the stage duration for each stage, let's say we give 20 days for the entire stage, out of which 15 days is putting up the form work and everything, laying out the ducts and all, and then pouring of the concrete, and then we'll give 5 days for curing of the concrete before we move on to the next span. And then we can also include the scaffolding reaction because it's movable, and include the weight of wet concrete for the subsequent stages. Then you move on to the section tab, and you can easily define here based on the section details for your center joint and the diaphragm sections. And then you can switch to the tendon tab, where the program proposes different type of tendon layout arrangements. So this is the one that that you can see right here. You can see how many number of strands you want or layers you want in each web, and you can very easily define the tendon profile in terms of multiplying factors of the length. So you can see them here. Now we will define the tendon properties. Now this is the interesting part, because I'll go and define multiple tendon properties, as I don't know which will be the best one for my job. So I'll select internal post tension, the material, and the total tendon area. So I'll start with a 0.5 inch strand. Let's say 19 in number to make one tendon. So I'll get the nominal area. I'll enter the duct area right here, select the relaxation coefficient, since it is low relaxation strand. So I'll select enter 2.5%, and then they are all bonded tendons. After this, I'll hit apply. The moment I do that, you can see the works tab is updated, and then I'll change the name to, let's say, web 2. So what I'll do is define like 4 different tendon properties and show you how to optimize your post tensioning. So I'll have now 0.6 inch diameter with 19 in number, and the duct diameter is 2.62. Apply. Then I'll use I'll change the name to, let's say, 3, and this 21 strands of 0.5 inch. Duct diameter, apply, and then let's say the last one is W4 with 0.6 inch strands, 21 in number, and the duct diameter has 2.75 inches. Then I'll hit OK. So we have defined 4 tendon properties here, and I'll start the entire bridge or all the tendons to have web 1 property, and I have the jegging stress as 0.7 times the ultimate strength of the steel material that we have used. So if you recall, the ultimate strength and the yield strengths are specified here. The friction factors, wobble friction factors, and the slips at the beginning and at the end are specified here, and whether the tendon is bonded or unbonded are specified here. So 0.7 times of the SU means the ultimate strength is the starting jacking value, and then the tendon scale can be laid out in different planes. So we'll have 2 planes in the web for post tensioning it. And then you can always save this wizard file for your future references. So you can just hit save as, and then you can save the wizard file with different names and options that you want, so that every time you are trying to create a similar project, you can just open this up, modify the parameters, and you're good to go. So once I hit OK, you can see the bridge is created right here, and in the works tab you can see all the supports have been defined. So I'll just display the supports. I'll display all the tendon profiles here. So you can see the tendon profiles. You go to the top view, the side view, and I can go to the front view, and I can make image files from here. So I can right click, say let this be my tendon layout image, and let me undisplay the tendons for now. Let this be the image for bridge layout, and I can cycle through the construction stages here. So this is CS1. What I'll do is fix the view and scale it down. And also I can display the point loads that are there. I can go to load, display nodal loads. So you can see this load is applied here as the next construction stage. The wet concrete will be poured, and it will be supported by the movable scaffolding system at this point. So this particular segment will get extra force here. So that has been taken into account. So you can save this as also as an image, and then you can change the construction stage and then proceed. So now the scaffolding has moved from this location to the next one, and the last stage is a null stage for now. So what we'll do is assign the duration to this last stage, as 10,000 days to see the permanent effect of creep and shrinkage to it. So let's start by defining the time dependent material property. So I'll go to properties, define a creep and shrinkage curve. I'll click add, quickly enter, this is C6000. Characteristic compressive strength is 6 ksi. The notational size for now, let's say 12. Show result, you can see the graph for creep coefficients. You can save that as a creep coefficient graph for your report. You can see shrinkage strain graph. You can click here, you can save that for your report, and then hit close here and OK here and close. Then we can define the compressive strength gain curve. Click add, C6000, CBFIP as the code. Here you have to enter the mean compressive strength of the concrete, not the characteristic compressive strength, so which is 6 plus 1.16. In Midas you can enter the numbers and operations anywhere, and the program will take care of that. So if I hit redraw graph, you can see the value is about more than 7, which is 7.16. I can create this also for the report graph and then hit OK and close. So I have defined the material, and now since the cross-section area I have not calculated, I let the program do it so that I can get the notational size for my cross-section to assess the time-dependent effect. I'll hit select all to select in the entire structure and then hit apply. So this has been done. Now I'll hit go to the material link and associate the time-dependent property that I selected or defined with for creep and shrinkage and compressive strength with the kind of material that I'm using, and then hit add. Once we have defined this, I'll hit close and the time-dependent material properties are set. Now I'll quickly define some superimposed dead loads because we need live loads and dead loads for optimizing the tendon post-tensioning. So I'll go to static load cases, enter a name, let's say superimposed dead loads, type being construction stage loads, hit add, close it, and now you can just click on element loads, and I can a new feature in Madisonville. Let me just close this and highlight it here. You can right click and select tree menu 2, so you can have 2 tree menus, and you can activate the works in both places. Now if I hit element tab, you can see the elements, the element beam load has been shown here, and I can use this works tab to make the selection, and then I can select the load case name and a group name, to assign it onto the structure. And the value should be 0.5 kips per foot, so I'll change the unit and adjust the scale accordingly, so the program updates it automatically for you, and then hit apply. So you can see the loading onto the structure. Now I'll close this, and I would add this load in the last construction stage, so which is of 10,000 days to see the permanent behavior. So I'll add the superimposed dead load on the first day of the last construction stage. This is done, and now we'll define the live loads onto the structure. Let me go to the initial view, and I don't need this table tree anymore, so I've closed it. Go to the top view so that you can see the definition of live loads easily. Now you can just go to loads, go to moving load, select the code here, select the line lanes, click add. Let's say lane 1, the eccentricity is 6 feet from the center line. All I need to do is just click here and then click all the way to the end, and here I can specify where my span starts. So I'll just check on those element numbers. and then hit apply. Then I'll define another lane, lane 2. Since there were 2 lanes on the structure, -6 is the eccentricity. Let me clean this table here, and then click on the last node. The program will create the lanes, and I'll just select the segments where the span starts. And then hit OK. And this way 2 lanes have been defined now. And next thing is we define the standard vehicle. So I'll start with H12 RFD standard vehicles with a dynamic load allowance, let's say 33% for truck, and then I'll use a tandem and then hit OK. So I've defined 2 vehicles. If you're using any other vehicle or any other DOT vehicle, you can define user-defined truck, train load, or permit loads. And we also have train loads built into the software, just for your information. Now I'll go ahead and define the moving load cases. I'll enter the name as moving vehicle load and then hit add. So the tandem vehicle will run on 0 lanes, then 1 lane, then second lane, then 1 and 2 combined, and then we'll get a set of results, and then we'll repeat this for the truck vehicle, and then the program will see out of these 2 cases whichever is the critical one and come up with the envelope at the end. So we have defined the moving load cases, and now we'll be defining the negative moment lane support. So I'll select the girder bridge. Now this is the step we are doing to optimize the vehicle position onto the truck, onto the structure, because the program suggests that truck should be placed in the either span, and the minimum distance should be 50 feet. So in order to incorporate those clauses, we have to do this step. Then I'll just define the lane reaction. For this, I need to know where my supports are located. So I'll just go to the secondary menu here and right click, display the supports. Let me unselect everything and just click on the next one, which is, so I have to specify where the interior support locations are, and I'll use single select to select those locations. There are 2 right there, and then hit apply. That's it, and click close. So having done this, our live load definition is completed and we are good to perform the analysis. So I'll go to analysis, set the moving load analysis control, set the construction stage analysis control, where you can consider the time dependent effects, you can consider the initial tangent displacement for erected structures, and then hit OK. Now you are good to perform the analysis. So I'll go ahead, let me close this one and perform the analysis. So while performing the analysis, let me save this more file as, let's say, RFP. And you can see the status bar is here. It will show you what analysis is being performed and what's the progress, so you can assess how much time it will take, and the time will be reported at the end of the table. So this is the analysis that we have done with tenant property 1. And we'll quickly see the results with that. So the analysis is almost at the verge of completion now. So this was the analysis that we done using the tenant property as web 1. So what we'll do now is see the results for the deflection and bending moment diagrams. So let me just go to side view
select, let's first define the load cases real quick, or load combinations. So I'll go to concrete and then select H2L RFP 2012 version and hit OK here. So based on the load definition, the program has defined the strength and serviceability load combinations. And for serviceability, we just need to monitor the primary effects. So I'll quickly modify them for the primary effects. So you can customize the load combinations in no time. So having defined this, I'm ready to see the results. So I'll right click, go to deformations and displacement contours, or the same can be accessed through our result tab at the top. So once we have reached here, let me first see the results for our construction stage analysis, and let me quickly undisplay the supports here. So this is the combined results. So I'll start with the stage 1 and we'll check on the deformation and displacement, and let me switch to inch. So this is the deflection that you are looking at. Let me just clear here. Alright. So this is the first stage. You can see the deformation is about 2.05 at the very first stage when we are just placing it and pouring the concrete. But once it matures, you can see the deflection is increased. It's about 2.36 here. And then you can go ahead and change the construction stage to second, third. And just to give you a better idea, this is the camber values also. So I can just control the scale factor of the deformation so that it becomes more realistic. So coming all the way to the end at the final step, this is the deflection diagram that you are getting. And here you can see the maximum deflection that is occurring and the deflection that is there. Now if we did not do the construction stage analysis and we have just directly come to the post CS, that is the post construction stage analysis, then we would have got something like this, which is pretty much regular, but the values are different from what you expect. And also if you see the bending moment diagrams, they are affected by the construction methodologies. So if I go to beam diagrams, let's go to say maximum bending moment without deformation. So you see such a symmetric bending moment distribution is observed, and most of the time what we misjudge is when we are doing the analysis, we model the bridge in one shot with the supports and just load and get the bending moment values and then design for this value. Whereas if you see the true picture is different. So if I go to the fourth construction stage and the last step, you see that the bending moment is distribution is a lot more different in the first span and the last span. The reason being the first span was very much simply supported when it was erected. And so this is the result that you can appreciate only through a construction stage analysis. And now we'll quickly focus on our deformation values for different runs. So this is the set of results that we obtained
from our when we are using the post tension as web 1, which is 19 strands of 0.5 inch diameter. The total tendon area was 2.9 square inch, and we have to check for the serviceability limit in order to get to the accurate or the exact result. So we are looking at serviceability results for load combination 5. I'll check on the deformed, and this is the deformed shape. We are getting a maximum deformation of 3.7 inches. Now what I can do, instead of proceeding with the design checks, I can easily go in and check certain things here. So first I can go and check the tendon losses for the end. Then I can also check tendon stress limits. So I can specify the tendon stress limits at different locations. These are the preset values to see if the tendons are yielding or not. And then but since the deformation is beyond my allowable limits, so what I can do is quickly go ahead and modify the tendon property. So if I come to the pre-processing mode, I can go to the load tab, select preset loads and tendon profile here, and then click change property. And since I want to evaluate different properties, I can just select and add them and just modify the property to property 2, hit OK, and we are good to verify the results again. So to cut short this the time for now, what I'll do is quickly open the results from the second run, and the time taken for this run was about 280 seconds. So it's less than 5 minutes. And let's see the results with tendon property 2 defined here. So you can verify which tendon property has been applied. And for this displacement contours, we'll use we'll see the deformed shapes. Right here. And let me set the scale as 0.5. So now you see the deformation for the load combination 5 has come down to 2.5 inches. So in this manner we can quickly assess that our post tensioning is working. We are able to control the deflection here, and you can also see the weight of the tendon that you are saving through this process. So you can go to tools or results itself and tendon, and then you have tendon weight, where you can just go to the tendon property and see the total tendon weight. So when we were using web property 1, we were having 60, the total weight was 67.3 kips, and this one is tendon property 2, which is 94.5 kips. And let me bring up the results from the third run. For the fifth case here, deform region, let me set the scale right. And then hit probably some good visualization here. And here you see when I used web 3, the deformation went high because the total tendon area and the weight would be less. So if I go back to the result tab and select the tendon weight, so you can see the weight is reduced, and so is the total force, and therefore the deflection is high. And so with the tendon property 3, we were getting this deflection. Now let me quickly show you the last tendon property results, and then I'll show you how we can optimize and reach something that is workable for us. So this is the fourth tendon property, and you can easily comment that, okay, yeah, if you increase the tendon area, force will increase, the deflection will decrease, and you will have to have more steel in it. So it's a very common judgment, and anyone can make it. But now the question is, out of all the different tendon properties, how we can quickly optimize to find which one should be the best combination. Shall we have all the tendons? Do we need same tendon size throughout, or we can play around with them? So the answer is we can play around with them, and let me first show you the results for the same load combination here. And you can see the value has sharply decreased with the tendon property 4, which is 2.27 now. So you can see with increasing tendon area, the deflection is decreasing. But now the question is to optimize it. So what I'll do in the same model, I know that my first span is showing the major deflection, and that is my concern. So I'll just increase the tendon area size in the first span, and then use a lower or less amount of steel in the remaining span. So I can either modify this particular model file, or I can open the one which has a lesser tendon value and then quickly modify it. So let me just stick to this one. Go to tendon presets, tendon profile, and I leave the first segment tendons as it is, but change all the others to a lower tendon property. Let's say I will select tendon web 2, click OK, and yes, and close. So basically we have now we have a combination of two tendon properties. We have type 2 and type 4, and now if we run the analysis and extract the results, you will be able to see the difference. Since we are just interested in looking at the results, let me quickly find the file, the root tendon properties in there. So I'll just stop this execution for now and open a new file with the optimization done. So you can cross-check quickly that I have used two tendon profiles, type 2 and type 4, and the results are as shown here. So I'll go to result tab, I'll go to displacement contour, I'll have combination as 5, formation legend, 5, click OK here. So now I'm getting the displacement as excuse me, let me change it to inches here, as 2.7 inch. So from we started with 3.75 and we came down to 2.7, so we were able to reduce the deflection by almost 1 inch, and being able to optimize the tendon pieces. Now this is a hypothetical problem that we investigated today, but it can the idea behind this is that you can easily modify your tenant presets and compare for yourself. And now the best part is the report generation. So for this, what I'll do is go to tools, and we'll have a dynamic report generator where I can easily open an existing template or create a new one. So I'll say open, and this is the final one that I'll be showing you. Let me open a template one. It's lying somewhere on my desktop. So you can create this kind of template, and the program will open Midas. Inside Madisonville, it will open a Microsoft Word page. So you can say, you can enter the company name as a header, you can enter the project name, the client or the consortium name for which you are working, and then at the bottom you can enter your engineer name, the number of page. And now all you need to do excuse me, go to the report tab, and let me see if we can quickly create some images for our bridge project. So like I was doing in the beginning, that this is my bridge. So let me display the supports here to get the bridge layout. And I'll right click and go to dynamic report image, bridge layout, click OK. Then I can just display all the tenant profiles here. And go to the side view, right click, tenant layout, and then you can prepare bill of material and keep it ready and handy. So for that you can go to tools, bill of material, click on bill of material. I'll just create of type 1 here. Okay, the program generates this kind of report with the bill of material showing you what kind of sections that have been used, what material properties are there, and what kind of and what is the total area of the concrete, and if it was if you need to paint the surface, what is the inner and the outer paint area. That's also given in this bill of material. So I can easily bring this bill of material into the report by either creating an image, and you can go to the report tab here and paste it at the point that you want to insert it. So let's start by quickly dropping and giving shape to our report. So let's say I want to have first the bridge layout, so I'll just drag and drop it over the screen. Then let's say I want to have my section data, so I'll go and have the section summary tables. So this intersection, the program creates this kind of section table. Then the other section, the joint section. So there are 3 different types of sections, if you remember we defined. And then we have the diaphragm section. We have defined here. And after this, we can insert that bill of material file here. So you can have the section and the bill of material right there for the sections, and then I can define the tenant property. So for this, let me pick the tenant layout, So you can see the tenant layout there, and after that you can let's go to result, tables, tenant weight for, let's say, by property. So now we have two tenant properties, 2 and 4. So program says that okay, for type 2 tenant you have to use total this weight, for type 4 you have to use this weight. Now you can right click, say dynamic report table, and then hit OK here. Then go back to report editor, and you can see the table is created right here, and then you can just drag and drop it onto the screen. You want to have, it's just like Word, you can format it by spacing them. This is the bill of material for tenants, and now based on your total concrete and tenant area you can enter the reinforcement as like 4% or 2% wherever required. So with little more information, and what I've done is generated this report, and I'll share it with you real quick here. So you can have something like this where you can show the bridge layout, the section information that you have used, the bill of material, then the tenant layout and the tenant placement, and then you can also show the construction stage. So CS1 stage, CS2 stage, I mean first stage, second stage, third stage with the load applied. So this way you can specify what construction methodology you are using, and you can also go and add all the results that you have used for. Now once we have satisfied with this pre-stressing, we can quickly do the design check. So I'll go to PSC tab and perform the design check here. Already all you need to do is just select the code, the parameter, so you can select between low relaxation strands and what kind of corrosion conditions are there, what is the flexure strength checks as per core or strain compatibility. The construction type can be segmental or non-segmental, so you can check these criteria and what you want to see in the output. Then you can define the material itself. So along with the material you can assign all the rebar information, and then you can go ahead and perform the analysis. And I'll not go much into the report generated because that is a topic we will cover up in our coming up webinars, but I'll quickly show you one interesting feature called PSC visual diagrams. So based on all the load combinations that are there, if I want to check whether my sections are safe or not as per bending moment about major axis for maximum minimum, thickness is 1, let's say, solid fill, and hit apply, the program will show me that this is the envelope that you see as green lines is the overall safety criteria, and the bending moment values are shown in the envelope form right underneath it. So this is a quick and crude check that okay, my cross sections are largely sufficient to handle this kind of stress and the post tension values. And then you can also put this, let me just undisplay the tendon profiles for now, and put that also in the report. Then I can just right click, dynamic report image, pre-stress design diagram. Okay, go back to the report and the report editor. I'll see another diagram created here, and I can just go and drag and drop it in this, as simple as that. So in this manner you can go ahead and modify your or do the optimization of your post tensioning. Now the last part was how to evaluate different construction methodologies. So what I'll do is open a fresh program right here. Close the things because I'm working on the network, so I don't want my system to slow down. Alright, so I briefly shared with you my work schedule for the day. So coming back to the program, I'll open a new file. Now with the same profile and same input, let's quickly create some other type of structure with different construction methodology. So let's start with the fully showed method of construction, which is very common. I can go in and just like previous time, I can define the material, define the concrete, the steel for the tenant, and then go ahead and enter the variables like 3 at 180 times 12 parameters if I want to enter in inches, where I want to have the fixed support, and what should be the anchorage, where the tendon should be anchored, and what should be the diaphragm thickness. All this thing can be entered here. Then I can define the tendon property. I can stick with that web 1 tendon that I defined, or this time I can have 2 and 1 combined. So you can define the tendon properties right here. Say this is 18. I'm just showing it to you as how you can define another construction methodology, but you can go and define the tendon properties which you have already finalized with that for that construction methodology, and then you can compare the results. So once you have entered these parameters, you are all set to hit OK and generate the bridge. Or if you want, you can save this and then open the one that you are working on and generate the bridge. Let me do that later. Let me just quickly show it to you. And likewise, I was also and in this manner you can create exactly the same bridge but with a different construction methodology, and the difference comes in the wet concrete weight. If you recall, the earlier we had a wet concrete weight coming at a particular location because of the movable scaffolding system, but since now the construction is fully showed from bottom, you have a fully supported system, so there is no need of extra reactions on the adjacent members. And let me display the supports right here. So this is the final arrangement of the supports: first stage, second stage, and third stage. And then you can have the fourth stage, and you can add the loads in the same manner. So in this manner, once the models are set up quickly, you can just in a matter of minutes you can modify the tendon forces and come up with a good result. Now in the same model, if I want to have a balanced cantilever approach, so I can go with balanced cantilever wizard. I can enter and punch in the numbers as per the same layout I want, and I can define in this pier section also. So I can go with the solid rectangle here, pier section. I can quickly enter the dimensions as, let's say, 72 inches by 18 feet, let's say, and then hit OK here, close, and it's a 3 span, so I'll enter number of piers as 2, stage duration like previous, but this will have different stage duration because it's a different construction methodology. You can choose cast in place, you can choose precast method, you can enter the section dimensions and the tendon layout. But for now, I'll just stick with the same tendon
property just for the purpose of demo here, and then I can hit OK to generate the bridge. So you can see the bridge is generated with the same profile, that is straight, with the sections that have been defined, but we have done the tapering because of the construction methodology. So this will affect my bill of material and give me the new numbers for my concrete area and my rebar area. Now, construction methodology selection also depends upon a lot of on the labor cost and the time invested, and the nature of site and the usage of the under bridge area. So depending upon those factors, the client usually recommends or put forwards a particular type of construction methodology, and until unless there is some significant saving or some another specific requirement, the construction methodology mainly remains more or less the same. So actually the engineers have to work in within very tight brackets in order to come with an optimal bill of material. And therefore, since concrete and steel, the cost of steel is much higher than concrete, so it is only the post-tensioning that they can really control and come up with a better or a winning combination of bill of material and the presentation. So also, if you want to have the same bridge with another profile, let's say curved bridge, so I'll just quickly open for FSM. I have an example ready here. Let me open that for you. Right here, so I have this example of FSM ready with me. I'll just open it. Everything is defined. I have entered the radius of curvature for this curved bridge to be about 7,800 feet. Then I'll hit OK here. And it's a very mild curve, so it can be sustained through a fully shored method of construction easily. And if you go to the top view, you can see the curvature. So in this manner, the key is how quickly you can simulate the model, because it's not a very detailed design. So all you need to do is come up with something quick to assess the behavior, and if you don't do the construction stage analysis, you will lose out on tendon losses, you will lose out on certain the force and the deflections in the structure, like I showed in the presentation earlier. So let's go back to the presentation. And let's see what we learned today. So I'm just summarizing all the things that we discussed. So the principal objective of design engineer is to prepare an optimal bill of material. And with bill of material, you can directly affect your bid. And since steel is more expensive than concrete, the post-tension optimization is the only key in this process. And using Madisonville, engineers can cut short the iteration process to find an appropriate post-tension. And you can also compare different construction methodologies in lesser time, as I quickly showed to you, and high quality reports can be generated as in the format that the client wants. So if the client has shared with you some kind of layout or format, then you can easily extract them.
So this was what we learned today, and let us quickly see what other companies are doing with Midas in the field of post-tension structures. So you can see a couple of projects that I've shared here, the ones done in Florida, Canada, Nevada, East Coast, West Coast for post-tensioning jobs. And this is the partial list of our existing users that are currently using Madisonville for doing their majority of the bridge related work. So once again, thank you for attending the session today. Like I mentioned, it was the first webinar of the series. We have 2 more webinars to come up. The webinars are based on the same line of post-tension box girder and different phases of the project. So today we covered the request for proposal stage, what elements of Madisonville can really help you out and update the process. And then the part 2 will be talking about how to optimize the detailed design using a common platform, so that we are not jumping on different platform for doing different things. You do for doing the superstructure, you need one set of design tool. Then doing the peer modeling, you need another set of tool. Then for your substructure, you need another set of tool. For seismic, you need third set of tool. So right now you are using 5 different products to accomplish one thing. So what you will be losing out if you're using such kind of approach, we'll be talking about that, and then we'll be summarizing as how everything can be wrapped up in the same project at the same time. So do join us for this session. It will be conducted on September 20th at 3 p.m. Eastern Standard Time. And the third part is a rather more interesting one. It is about load rating, and load rating sometimes could be very critical. For different components of your bridge, you need different type of models. Sometimes you are good with spine models. Sometimes you have to use grillage model for rating different components. So we'll be talking about when to use what kind of model for different component ratings. We'll also be talking about how you can cut short the repetitive process of finding the tonnage using spreadsheet. So all this will be discussed in the last webinar of the series that will be done on September 26th, 2012 at 3 p.m. EST. That's a Wednesday. So do join us then. And for both of these webinars, we'll be using the latest AASHTO codes that are out early this year. If you have any questions, comments, or feedback, please feel free to share with me. The presenter of the day was Arun Sharma, and my phone number is 646-852-9292. And you can also send me emails for your questions at asharma@midasuser.com. Once again, thanks for joining in today. This is Arun Sharma signing off from MIDASoft. Have a great day ahead. Thank you. Bye-bye.